So let's consider task number one sample test when we have a sample and we would like to know if the sample came from a population with expected properties. And in parametric way, most of the time, these properties mean, because we are interested, first of all, about the center of this sample of this population, right? In the parametric approach, the parametric solution for this task will be using one sample t-test for mean. And the non-parametric method, it's called a Wilkinson sign rank test for the median. So let me show you how it works. In this case, I decided to use dataset, which is not good for non-parametric tests. It's designed for the parametric approach because it follows normal distribution. But the reason why I'm doing that is just to show you also the difference between parametric and non-parametric method. Okay. So I used examples that I also used in second learning sequence of block number 2. It's about the tablets. It's about how long tablets can work without recharging, right? So in this case, that company claims that they work more than 20 hours. Customers complain that it's not. So our goal is to find out if it's true or not. Okay. So that was our initial null hypothesis. Although we trust our tablets, we still have null hypothesis, no effect, is that our tablets not as good as we actually expect. We follow the claim of our customers, right? And then our null hypothesis is that the average time, working time is below 20 hours, right? Then we have the alpha, then we have the sample size, and this is the sample. So this is the result of test of 10 tablets. This is how many hours they worked just by watching YouTube videos with 50% screen brightness. Okay. So and then remember, the parametric approach would be to make a t-test. So we compute average, we compute standard deviation, we compute standard error, and then we compute t-score, first of all, how far the average that we observe is from the average that we expect, and then we can compute a p-value based on t-distribution, right? And then based on this test, actually, we found out that we need to reject null hypothesis because our p-value, the evidence is against the null hypothesis. That was the story. Now let's try to apply a non-parametric method. So, and then I will use it also to explain how it works, all the details. So this is step-by-step guides how to run the Wilkinson sign rank test. In general, of course, you will use the software, but it's nice to know what's going on inside. The idea is following. First of all, you test for median, not for mean. Then you compute a difference, how far your values go from the median. And then you exclude all values if difference is 0. So if you have a 0 difference, simply remove these difference values, and then you have new sample size. Without this removed values, it's called NR. So this is just a reduced number. Okay. Then we assign a rank to every absolute difference. So we compute, we forget about sign and assign a rank to all this difference for smallest to largest. Then we assign a sign as well. Then we compute sum of positive ranks, sum of negative ranks. Then we take the biggest of these two and use it to get a p-value. Let me show you step by step. I use this data set, so this is time. So this is the values, the time of tests, how long they worked, the tablets worked. And then in this case, I changed the null hypothesis. The median time is below or equal to 20 hours, right? I actually probably also need to set the alpha. In this case, I will use alpha equal to 0.01 just to have a direct comparison. But in general, you will learn also in this learning sequence, the non-parametric tests have a smaller power. So in this case, the alpha, using alpha 0.01 requires really, really big sample size, but we will discuss it in a minute. So the first step, take a difference between the values and the tested mean, right? So we find a distance, how far every value is from the tested median value, median, not mean. And then you can see, for example, why this is minus 0.3, because it's 19.7 minus 20 minus 0.3. 21.5 minus 20, 1.5. 23.3 minus 23.3. That's it. So these are the differences. Now, if we forget about sign of these differences, we can make also the rank table, right? For example, without sign, this is the smallest absolute value, 0.2. This is the smallest distance we observe, and that's why it has a rank 1. Then the next smallest distance at 0.3 also has a rank 2 in this case, and so on and so forth. So you can see that every distance now has a rank. But when we compute rank, we don't take into account the sign. Is it negative or positive? Only absolute value. Then we recall that we also have sign. So we have 3 distances with negative distance, 3 distances are negative and 3 distances are positive. And after that, we split the rings into 2 groups. The blue group, it's the negative rings, and the red group, it's the positive rings. And then we simply compute a sum of rings in each group. So for example, in case of the positive rings, you can see we just need to take this, plus this, plus this, plus this, and this, and it gives us 49. Instead of, in case of negative rings, it gives us 6. So it's 2, you can see plus 3, plus 1. And therefore, if we want to take the biggest of these 2, it will be, of course, 49. So this is our test statistic, and this statistic we need to use to compute the p-value. Now, if we want to use this statistic, we need to know which distribution it follows, right? Well, we know that sum of values, in general, sum of values follow normal distribution. If you have large enough values, like 20, 30 values, then sum will follow normal distribution, okay? And indeed so, the V statistic that we computed follows normal distribution approximately, not precisely, but approximately. However, the number of distances should be at least 20. And in our case, we have 10. So therefore, this test will not be very precise. But nevertheless, let's compute the p-value. This is the expected V. So if our null hypothesis is true, then this is the expected average of the V statistic, right? And you can see that it depends on the sample size. This is the variance. Again, we computed only based on the sample size, so that's why I use sigma and mu. It's indeed for population, it's expected value. So this is expected value for your future sample, right? And then let's do this computation for our case. So in our case, we have, this is the sample size, 10, we don't have any 0 distances. So this is our statistic, 49. So let's see the expected value. What should we expect from 49 if null hypothesis is true? So in this case, we compute mean. You remember NR is equal to 10, so we have 10 times 11 divided to 4. This is 27.5. So you can see we have 49, but it's 27.5. It's pretty larger. It's pretty far away from the expected values. But how, is it a big distance or not? We don't know, because we need to compute standard deviation, standard error, in order to find out how big this distance is, right? So first we compute variance by just putting the 10 to this, and it will give us 96.25. And then we compute standard error for V statistic by taking square root of the variance. It's 9.8. So you can see it's approximately 10, right? So 27 plus minus 10 in 68% of the cases, 27 plus minus 20 in 95.5% of the cases. And you can see that our value is still beyond the 27 plus minus 10, right? So it's still larger. So we can assume that our V value is quite extreme. But how extreme? Well, we need to make a test, right? First, we compute z-score, how far, how many standard errors we have between the observed V value and the expected V value, which is in our case 27.5. And then you can see it's 2.2 standard errors approximately. Because it's a one-tail test, it's a right-tail test, right? You remember our null hypothesis is that the median should be below or equal to 20, right? So this is the right-tail test. So therefore, we need to compute the area on the right of this z-score using the standardized normal distribution. We know how to do it. Because it's area on the right, we take 1 minus p-norm, and this is the z-score, and this is the p-value. You can see it's 0.014. And then again, if you look at this p-value, we cannot reject null hypothesis in this case if we work with alpha equal to 0.01. So in this case, as I told you, that the non-parametric approach, they need a bigger sample size in order to get the same evidence as the parametric approach. Okay. Now let me show you how to do it in R. So this is, I just enter the data, all this data, and then the function that does this test in R, it's called Wilcox test. You need to provide the values. You need to provide parameter mu, although it's not mu, we know it's median, but that's, I don't know why they still call it mu. And then we need to provide that it's a one-tail test, that alternative is greater, right? You remember the null hypothesis is that median is equal or above median 20, and the alternative will be therefore the median is below 20, right? Or vice versa. equal or smaller, and it's greater, right? That's alternative. And then you can see the output. So this is the data. This is V value. You can see it's the same as we have. And the P value is actually also the same. You can see 0.014. So in this case, we can see that our calculations were correct. And then you remember that if you look at the t-test, you can see that the t-test p-value is smaller, right? Also, you can see that in t-test, you have test for mean. Here it's called location. Location is greater than 20, right? It's location of the center. So it's sometimes it's median, sometimes it's not median, but in the non-parametric approach, it's most of the time it's median. So you can think about this as a test for the median of your sample. Okay. So that's how it works. And now, once again, all non-parametric tests have a smaller power. So it means that if you have an effect, it will require much larger sample size. Not much maybe, but larger sample size comparing to the parametric approach. So therefore, the parametric approach is better from that point of view, so you can use it for the smaller sample size, so you can save some resources, right? So if you can use parametric approach, use parametric approach. If you can't, then use non-parametric, but make sure that your sample is large enough. Usually it's 20 or more. Sometimes some tests work well with 10, but usually it's 20 or more. Okay. So that's done. Now we know the non-parametric way to solve the one sample test problem. So if you need to make a test about the location of the center in one particular sample and one particular population, in the next video we will discuss how to compare two samples and two populations.